What I'd like to do for the next 20 minutes is give a high-level overview of some of the exciting projects and programs that we have at SDSC. So the title here is Gateways to Data-Intensive Discovery. You can see it in our banner overhead. I want to decode that a little bit for you. There's also a subtitle here which says providing an end-to-end computing ecosystem. We've done that at SDSC and we are reaping the benefits of that integration. And in my talk and in subsequent talks, you'll see that elaborated in some detail. Okay, so let's start with data-driven discovery. So it has been in the news a lot, and here I've just grabbed a few press releases from our own website, but all of these things have made national news. The discovery of gravity waves by colliding black holes. There's an article there about the fact that a third of the internet is being hacked at any given time. There's a discovery of a much broader tree of life than we ever knew about before, using metagenomics, phylogenetics. And then finally, the discovery of a neutrino from the edge of the universe, a high-energy neutrino. And while these may seem like, the kinds of science discoveries you expect to read about in magazines, what is unifying about them is they all were enabled by our HPC system at SDSC called COMET. So COMET is really at the nexus of multiple research cyber infrastructures that I'll be talking about. Of course, it is an Exceed resource. It provides computing for the Longtail of science. It also is integrated with the Open Science Grid, as I'll mention. It is, of course, a workhorse for a majority of the NSF users. So I want to go into this notion of Longtail a little bit. What you're seeing here is an analysis we did in 2012 of the workload on the entire Exceed project. And what we found is that 99% of all jobs were of size less than 2,000 cores. 99% less than 2,000 cores. And those jobs comprised more than 60% of the total utilization. And so we were writing a proposal for the next system that became COMET, and we said, why don't we architect a supercomputer to serve that community? That's what we mean by the long tail. So as we were putting together this proposal, we had a number of governing ideas, and I just want to walk through those for you. First of all, architect an HPC system where those 99% could fit into a single rack. Second, increase the memory per node so that parallel jobs could compactify. A lot of the reasons why parallel jobs use a lot of nodes is to just grab the memory they need. You put a lot of memory on a node, you can contract in the parallel dimension and achieve higher performance as a result. Number three, and this is a policy decision, embrace single core and single node jobs. Previously, supercomputer centers were all about the high end. And if you had a large parallel job, you got preferential treatment. We changed that with COMET. Single core, single node jobs are first-class citizens as reflected by our scheduling policies. Number four, support gateway access. Gateways are web portals that connect users to computational codes running on COMET. And gateways were not new when we wrote the proposal, but they were an increasingly important kind of way that people access supercomputers. So we wanted to make COMET the best gateway resource in the Exceed program. And we accomplished that, by the way. Number 5, provide research communities, fully formed, fully capable research communities, control over their software environment through virtualization. And this was a decision we took before Docker, before Singularity, before any of the containerized solutions existed. So this was really thinking out of the box. And number 6, and this is also a little non-intuitive, underallocate the resource so that high throughput jobs could get high throughput. Okay, so 4 years later, Comet is fulfilling all of those design goals, and it is at the nexus of the Exceed user community, the Open Science Grid user community, gateway access, and what's new at this conference, we can announce that we have integrated Comet with the cloud, Amazon Web Services. We can cloud burst from our scheduler into instances in AWS. This is a pilot at this phase, and we are looking for volunteers to work with us to develop this further in terms of what kinds of applications, the data movement associated with that, what instances in Amazon are worth connecting to, and so forth. So you'll see a news item on the Exceed user news posted just last week. If you're interested, please let us know. Okay, so let me start going down the list of these capabilities, starting with gateways. As I said, gateways are web interfaces to HPC codes running on supercomputers. And they simplify the use of those codes by a point-and-click interface. Here I'm showing the Neuroscience Gateway, developed at SDSC by Amit Majumdar and Suba. I don't know, the Suba's sitting over there. I still can't pronounce your last name, but so Suba. This is a gateway that is growing in adoption that makes codes that simulate real neural networks. I'm talking about the kind in the brain available. This graph, which is probably inscrutable from where you're sitting, shows the usage of the entire Exceed set of resources over a 5-year period. And the significant thing is that this yellow line is gateway usage in terms of users. This line here is the total, which is gateways plus login users. And now gateway users outnumber login users by a substantial fraction. You might wonder, well, what was this huge uptick that occurred in the fall of 2016? That was bringing the ITASR gateway online. ITASR was not developed at SDSC. It was developed, I think, at Michigan, University of Michigan. Is that right? And this is by far the most popular gateway for protein structure and protein function analysis. Here is a list, too small for you to read, of all the gateways that are using Comet at the present time. Last count, 80% of all gateway usage across Exceed is being done on the Comet resource. And part of that is the architecture and the scheduling policies that we've adopted that make these highly interactive computing environments. It's really interesting to look at the fields of science that these serve. So system biology, neuroscience, chemistry, engineering, biochemistry, biophysics, earth science, basically anything you can think about either has a gateway already developed or they're developing one, which is a natural seg into an advertisement for a talk that will be given by Nancy Wilkins-Deere and Michael Zentner on Wednesday, afternoon about the Science Gateway Community Institute. This is one of the NSF's 2 science institutes that are funded at a high level for the entire national community, and this one is focused on the incubation and development of new science gateways. This is led out of SDSC, but it involves partners at Indiana, Texas, and other places, Purdue. So this is a great community resource that will help you create a gateway which could run on Comet. Okay, end of gateways. Now let me talk about the Open Science Grid. If there's one thing that I've done as the director in my 10 years at SDSC that I'm most proud of, that I think is the most significant thing, that is the full integration of our resources with the Open Science Grid. Why is that? The Open Science Grid, which is directed by Frank Worthvine, sitting over there, who is a UCSD physics professor, and the next speaker, so don't go away after my talk. The Open Science Grid is how facilities compute. They don't come to exceed. We don't offer the right kind of computing. And we're not connected in the right way to all the institutions that are involved in these big experiments. So the Open Science Grid, I call the second national research cyber infrastructure. And what I did, I don't know, 6 years ago now, Frank and I had a lunch with the guy that runs computing at Fermilab, and we started down the path to integrating OSG with TeraGrid and now Exceed. So that has been a wonderful thing. Now, the way we did that technically is using the virtual cluster capability that I mentioned earlier. Again, this is before container virtualization. This is the ability through virtual clusters to just take a chunk of Comet hardware and give over its software environment to a team to do with what they will. And in this case, the team was the Open Science Grid team who put their full stack inside a virtual cluster which can be spun up or spun down at any time. That means any instrument, any program, any researcher using the Open Science Grid can flow to the Comet system for their research. Well, this paid off with the discovery by the LIGO Observatory of the first gravitational waves in the universe, a discovery that led to a Nobel Prize, not for us. We're just the handmaidens of this, but we devoted almost 1 million core hours to the OSG work that was done in mid-2015 to verify that first detection. So virtual clusters made a contribution to the discovery of gravity waves. Very proud about that. And Frank, in his talk, will talk about some of the other projects that I showed on that slide. I want to turn now to a different program at SDSC. This is a new program called the Data Science Hub. SDSC has 250 people in it, and the majority of them are grant-funded researchers who are doing all manner of things in application and software development. And the center of gravity of their expertise is in data science and data science engineering, databases, workflows, all of these things. And so the Data Science Hub is the entry point for any resource, expertise, collaboration that you might want to have with SDSC. It is directed by Ilkay Altintash, who will be speaking here in the booth tomorrow morning at 10:30. She will be introducing the Data Science Hub in more detail than I can do here. But it is our newest initiative to engage this new world of data-driven everything, including machine learning, artificial intelligence, and so forth. This is just an example of what they do. This gets to end-to-end integrated solutions. This is a screen grab of an app called FireMap, which provides real-time information to the firefighters who are very busy right now in California. This is the fire that's near Malibu. This system allows firefighters to track the growth and predict the growth of the fire perimeter using satellite, ground-based, and now drone information, all integrated into this cyber infrastructure, which, by the way, has HPC on the inside. What I mean by that is they can run a quick and dirty kinematic fire model to predict in almost real time how this perimeter is going to spread. And so the firefighters have their tablets, they just drop a spark somewhere, they hit go, and it tells them with the prevailing winds and the fuel source how that fire is going to spread. Turning now to a different program, which is actually an entire division at SDSC. They have designed, built, and operate the Sherlock Cloud, which is a cloud designed for compliant data management. And they have a full stack set of services that come with that. And just last year, they made an integration with Amazon. So now it is a hybrid cloud that has the capabilities of our on-prem team and services, but has the elastic scale-out capabilities of Amazon. And they are currently working on integration with Azure because actually the logic is very simple once it's explained to you. Who has protected data? Hospitals have protected data, HIPAA data. What software do they run on their computers? Microsoft software. So those customers want integration with Azure, not Amazon. So we're working on that. The last topic I want to mention is our robust industrial program, and Ron Hawkins is on the calendar. He's speaking later on today. He's chairing a 1-hour session from 3 to 4, where a subset of these vendors will be presenting. Now, as you look at this logo cloud, you see a variety of computer and technology vendors, but you also see end users like Janssen, which is the R&D arm of Johnson & Johnson, Genomic Science, SDG&E. They are a partner. Why? Because they care about fires in the backcountry. That's where their power lines are. So they're part of that project. And we've got Scripps Research Institute, a massive research institute, also biomedical research. And so we have an interesting industry program where you've got the technology, the solution providers eager to put their stuff in front of end user businesses. And end user businesses who come to us to see the future. And so Ron has crafted an industry program that brings these two kinds of industry partners together, and we are a neutral place where they can work in a pre-competitive way together. And an excellent recent example of that is something that we just kicked off called Block Lab. There's all this buzz about blockchain, right? Blockchain is going to solve all the world's problems and no one will have to write a line of code. That's just like quantum computing, by the way. It's going to solve everything. Just wait. Anyway, I'm putting my money on blockchain in the near term. And so this is fundamentally a sandbox at SDSC with industry partners who are themselves exploring the uses of blockchain, and they want to find out what others are doing and do it in a pre-competitive space. So I don't know that we have a presentation on Block Lab at this in this booth, but you can always grab Ron and ask him about it. Okay, so last slide. I just want to thank our sponsors, some of whom are surrounding us here. DDN is sponsoring this morning session. Thank you, DDN, and thank you for turning off the sound. Dell EMC, of course, our partner with Comet, Intel, Eon, Gig.io, and Weka.io are presenting in the booth. That's very interesting work. And then NVIDIA, of course. I didn't mention that Comet has the most GPUs of any Exceed resource. And one of our motivations for cloud bursting to Amazon is to get access to even newer generations of GPUs in the cloud. So with that, I'll stop, and
Time for questions, Mike?
I guess we have 5 minutes for questions. Thank you. Thanks very much for attending. Thank you.